Okay, good morning. I'm Harry Atwater. I serve as editor-in-chief for the journal ACS Photonics, which together with the Meta 17 conference has sponsored the ACS Photonics Meta Young Investigator Award. And after evaluation of a number of very competitive applications from all over the world in our field, I'm pleased to announce this year's award winner, which is Professor Dirk Englund from MIT. Dirk is somebody I've known for a while, since he was an undergraduate at Caltech, where he earned his bachelor's degree in physics, then earned a PhD in applied physics from Stanford, and then was a postdoc at Harvard before going on to a faculty position at Columbia before arriving in 2013 at MIT. More than any of the young investigators that I know of, Dirk really exemplifies the combination of use of very leveraging technologies like silicon photonics and very innovative thinking in his area of interest in quantum information and quantum communication. So he'll be talking to us today about scalable semiconductor quantum networks. So I want to invite Dirk up to the stage here to receive this award. And the citation reads, "Given in recognition of his pioneering contributions to scientific research in the area of quantum information processes and communications." So,
thanks so much.
Congratulations,
Thanks
Dirk.
so
Okay.
Thank you.
Okay. So I guess we have to pose for a more suitable picture here. So let's. Okay.
Harry, I want to thank you and everybody at ACS Photonics so much for this terrific recognition. And I want to say that obviously this wouldn't have been possible without dedicated and hardworking students and postdocs. And so really, I think I'm going to have to take them out for a lavish dinner when I get back to the States. All right. So good morning, everybody. Thanks all for showing up pretty early here. I'm in a completely different time zone. I don't know about many of you, but I want to tell you this morning a bit about some of the work that some of my students, share this credit for on building devices and protocols and systems for distributing entanglement across networks with applications for cryptography and things like modular quantum computing as well. So I want to start, though, with a simple shell game. And this is a shell game in a classical world. And as we all know, the classical world can be sometimes fairly boring. And so the game goes like follows. So Alice and Bob both have a box, and you put a coin into that box. The coin can either have heads up, let's say blue up or red up. And you can look at it in two possible ways. For example, maybe there's like a prism on it or something, so you can look at it from the front, or you can look at it from the side. You put Alice and Bob put the coin in the box. They shake it. They look at it in one possible way, either from the front side or from the side door. And suppose that they're separated. And so, not surprisingly, in the classical world, sometimes if Alice looks in the front P door, for example, she sees a blue coin up. And Bob might randomly also see a blue coin up if he looks in the same door. If Alice and Bob look in the other door, they might get red up, blue up, and so on. In other words, in a classical world, the outcomes of this classical particle of measuring it in two possible ways is completely uncorrelated, and it's pretty boring. But suppose that we have a quantum particle, and that might be, for example, an electron spin, which can have two possible states if you measure it along a magnetic field, either spin up or spin down. And you can measure it along two possible magnetic field directions. And we might call those the measurement of P, for example, with the magnetic field in the Z direction, or Q with the magnetic field in the X direction. And these are not regular spins. These are actually entangled. They've been prepared in advance. in some way, and then the measurement actually looks very different. So suppose, again, you tell Alice and Bob, look at the spin in two possible ways, either in the P measurement or in the Q measurement. And if the spin was prepared in the right way, then you have these interesting results that if Alice looks at it in the P door and Bob does the same, they both get blue side up. If they look in the Q door, they might both get the red side up. Or at random, they might both get the blue side up. Any way they measure it, they locally get a random result, but the result is correlated with the other partner. And so this is pretty curious, right? Because now the information is stored in the correlations. There's no information encoded in the into the spin locally, but there is in the correlation between the two measurements. So now they get suspicious. Hey, what's going on? Maybe if Bob measures in door Q, that somehow sends a secret message that we can't measure over to Alice's setup, which flips the spin just in time so that if she looks in door Q, she also gets the blue side up. Well, this thing, you'd be really surprised if this thing persisted, even if Alice and Bob are so far away that their two measurements cannot be affected by a speed of light traveling pulse. For example, if Alice is on the Earth and Bob is on Mars, and they still get these same correlations, then there's no way that some message passed from one setup to the other in time to switch the state of the coin. And that then becomes really spooky, and Einstein famously referred to this as spukhafte Fernwirkung, or spooky action at a distance. It doesn't have the same ring, I think, in English. But this was a big puzzle, and it points to the fact that, in fact, the physical state of these two particles is, in fact, correlated, even if they're very far apart. So there are non-local correlations between the two particles. And this paper was intended to sort of ridicule physics, that notion of this non-local correlation, in 1935. But there have been a number of experiments, as most of you know, of course, that have closed any possible locality principle that would explain this. And in fact, in recent years, even this communication distance loophole was closed. And so what could these particles be? Well, they could be spins. They could also be photons. So suppose that you had an entangled photon pair source that produced two photons that were entangled in the polarization degree of freedom. And so what that means is that the measurement for Alice, for example, could be either she measures it in the horizontal vertical axis. So for example, here she makes a measurement in the horizontal axis. Or she makes a measurement in the diagonal axis, okay, diagonal 45 and diagonal minus 45 degrees. And what it means is that if she measures a particle in the horizontal vertical axis that's, for example, vertically polarized, then that projects Bob's state into the vertically polarized state as well. And that's the correlation. So they can use, for example, entangled photons to produce these correlated outcomes. They're random local, but they're correlated at a distance. And so that's basically the underpinning of why we're interested in, a large reason of why we're interested in quantum networks. So in a quantum network, you would have, for example, Alice and Bob, just, some distance apart. Maybe they are, maybe they're in the same locality. Alice and Bill would be within maybe 50 kilometers. In this case, you can send photons between the two of them and build up these quantum correlations. And again, since these correlations are random locally, but correlated at a distance, they could use these correlated measurement outcomes as random but shared key between them, for example, as a way of doing one-time pad encryption. As soon as they have a shared secret, in this case, the measurement outcomes of the photons in the two possible basis states, they can use that as a way of cryptography. So they can do that locally if the distances are short enough so that a photon can pass through with some efficiency between Alice and Bob. But if they're far apart, like in this case, for example, maybe some thousands of kilometers, they might need different ways of producing this entanglement. But at the end of the day, it's the same thing. You just need to find some way to produce entanglement between Alice and Bob. And then you can use that for a number of applications. I already mentioned that you could use it for cryptography or secure communications. People are interested in using this for studying foundational principles of quantum mechanics. You can do a number of other things that the community is investigating, like networked quantum computers. if, for example, Alice and Bob had not one electron spin, but a number of electron spins that they can manipulate and so forth, they would have locally a small quantum computer. And then by networking these quantum computers together, by using these entanglement correlations, they could build a more powerful computer. In principle, every time you would put two computers together in this way with enough feed-through entanglement rate, they could be exponentially faster. Blind quantum computing is another area of interest that people are looking at, like Philip Walter, who's in the audience. There's ideas for using these kind of quantum networks for quantum sensing, for very precise timing and very precise GPS. And there's probably a number of other applications that we simply yet don't know about that these kinds of quantum internets could enable. Okay, so, but let me start with the first one, okay, with the metropolitan scale or with the short range distance network. So here, again, the problem is somewhat easier because Alice and Bob just need to pass between them some photons to produce these quantum correlations. And that's really the basis of quantum key distribution. They normally don't use nowadays in quantum key distribution entangled states. You can simulate an entangled state if Alice just pretends like she was measuring one of her photons in a random basis and then sends the other photon over to Bob. It comes out, but the security proof for these QKD schemes is though still based in the same entanglement principle. And there's a number of companies that will now sell you, if you have enough money, a quantum key distribution system, ID-Quanti, Quantum CTEC. There's a number of networks being built in Europe, in the United States, in Asia. This one actually breaks out of this metropolitan scale distance. This is, this famous satellite from the group of Zhenwei Pan in China that recently, in two important papers, showed quantum key distribution and also teleportation between two faraway telescopes using a satellite in which two entangled photon pairs were produced and beamed down to Earth into the two satellite receivers. Now, all of these have the commonality that the loss is relatively small. The optical loss is relatively small, maybe 50 dB at worst, so that photons, when you send a photon in, there's some chance that we'll make it out the other side. But if the, and so I want to talk about that first, but then later think about how we might bridge longer distances. So we in Boston, with collaborators, have also been interested in building some small quantum networks, and here's just one example. Where using a high-dimensional encoding that it's not really necessary to get into in detail, but basically using an encoding of photons in a basis state that's not just 2 in size, but in this case can be up to thousands of basis states. This large alphabet encoding allowed us to set sort of a record actually over a 42-kilometer relatively lossy 15 dB fiber link between MIT's main campus in Cambridge and MIT Lincoln Laboratory in Lexington, Massachusetts. So we can get about a megabit per second over this fairly lossy fiber. That's not super fast. It's about as fast as my American Comcast service, which is terribly slow. So it's important to think about ways that we can maybe speed this up. And I just want to tell you in passing that in my group, some of the things that actually Harry mentioned, we're working on these silicon photonic circuits. So we're using foundries to build these silicon photonic integrated circuits that squeeze light into these small waveguides of silicon surrounded by glass. And these foundries will give you a lot of really fancy tools to build, for example, switches and modulators that are high speed and low loss and so on. We've integrated superconducting detectors into these devices. And we can build some reasonably good transmitters for quantum key distribution to speed up the rate of Alice's transmitting of photons over to Bob. So for example, here you see a large circuit that's complicated, but basically it has these, like a bank of 48 traveling wave modulators together with a bunch of input grading couplers for lasers, output grading couplers for how the modulated light comes out, and phase modulators and wavelength division multiplexing elements. So here basically this is a way that we can encode QKD signals over 48 or so spectral channels. Each of them, well, we're not yet ready with this device, but we're starting to plug it into our network. Each of the channels should produce some megabits per second, and so you can get to maybe 50 megabit per second or something like that, so maybe 100 megabyte per second key rate in a metropolitan network. So this is, I would say it's been a lot of fun for us, and it helps in the short term, but it is a brute force approach. Basically, we're just sending light faster to Bob, but at the end of the day, all quantum key distribution protocols in this way that don't use repeaters have this commonality that the rate at which they can produce secure key, okay, drops exponentially with the loss in the network, okay? So at the end of the day, you will lose. It doesn't matter how good your transmitter is, doesn't matter how good your protocol is. If you don't use a repeater, you probably just can't get respectable rates over some hundreds of kilometers of distance. So how do we get around that? How can we build a sort of quantum internet to produce that entanglement between Alice and Bob, maybe on the continental scale or so? And the idea is from Hans Briegel, from 1998 already, and it goes as follows. Suppose that you had stations where you have some quantum memories, let's say electron spins again, right? And these stations are relatively short distance apart, so that photons do cross that with reasonably good efficiency, let's say like some tens of kilometers. Then what Alice and Bob could do is they could tell everybody in the chain, okay guys, send photons to the nearest neighbors and use those photons to entangle electron spins in your nodes. Okay, and so that happens with some probability. You might have to send photons many times, but ultimately each of these channels will be bridged by photons because they're relatively short, and so you can produce entanglement between, let's say, stationary electron spins in this station and in that station, and then again in this station and in that station, and so on. And then using local quantum operations, entanglement swaps, you can ultimately share entanglement between Alice and Bob, even if they are some distance apart. That would never be possible to bridge using just photons. Okay, and so what do these stations look like? Well, each station needs to have some stationary memory, like an electron spin, and I'm indicating that here as a black circle. Each of these electron spins has to couple to a photon so that we can entangle the electron spin to a photon, send that over to the other person to generate that entanglement across the two stations. And so you can see that, for example, here. So normally these interfaces between the electron spin and the photon are inefficient. So it helps to put the whole thing in a cavity, like I'm indicating here. That makes the spin-photon interface more efficient. And then at the minimum, you need to have two qubits or two electron spins in every station, so that this station can be entangled with that station, and that station can be entangled with that, right? So it's at least two per station are necessary. But in reality, you probably want to have a couple of pairs of qubits in every station, so that it helps in error correction. There's a number of reasons you need this overhead capacity. And so basically what the quantum repeater is going to have to look like for distributing this entanglement is some sort of a box that contains multiple electron spins, let's say, or other types of stationary qubits that are with reasonable efficiency coupled to photons. Okay, and that's essentially what in my group we're trying to build for repeaters. And basically our circuit in our case looks like an optical circuit like this one. These false yellow lines indicate waveguides that are intended to connect together a bunch of electron spins, which in turn are, in our case, they're nitrogen vacancy centers and diamond provide these electron spins, and they are in turn coupled to these photons, to these waveguides. And then here I want to talk about two applications in quantum communication and further in building small-scale modular quantum computers. And so, what I'll talk about is sort of this architecture with the spins and our photon resolving detectors and so on that we need, and then these two applications that this architecture may be useful for. And so the people who contributed to this work in my group are these graduate students and Tim Schröder, who's an assistant professor now at the Niels Bohr Institute in Copenhagen. And we've enjoyed a lot of collaborations that have made this work possible, and I should also credit funding, of course, as well. All right, so what's our electron spin? We can't just hold electron spin in space. Some people do that, in ultra-cold atoms. We're interested in using semiconductor materials to hold these electron spins. Now we have to couple this electron spin to a photon somehow. So a good way to do that is to put the electron spin into some sort of an atomic or atom-like emitter that has spin-dependent optical transitions, so that the photon can be in a ground state and an excited state, and going between them means that it's coupling to an optical excitation. And the NV is one of these kind of atomic emitters, one of a variety of emitters that people around the world are investigating. So the nitrogen vacancy is a nitrogen atom substituting a carbon atom in the diamond lattice, which you see here, adjacent to a vacancy in the diamond lattice. And it's a reasonably good emitter, so if you do photoluminescence of a diamond sample, even natural diamond sample contains actually a reasonable abundance of nitrogen vacancy centers. And you'll see if in a photoluminescence scan, you might see something like this, where when you pump with green light, you sometimes get red fluorescence out, and it can be localized in this way, so to a diffraction limited spot, let's say a micron or so in area, and that corresponds to a single color center, a single nitrogen vacancy color center. Now, the special thing about the NV, when it's in the negatively charged state, if you add an extra electron to the nitrogen vacancy center complex, is that the ground state of the NV has two unpaired electrons to start with, and these pair up in the ground state into a spin triplet that you can see here. So two electron spins either being parallel up or being parallel down, or up, down, plus down, up. Okay, these are the three magnetic sublevels that are possible in this NV center in the ground state. Now the thing is, when you put two electron spins nearby, let's say some sub-nanometer distance, they will interact just like two magnetic dipoles would. And if you calculate, the interaction, the magnetic dipole interaction, it amounts to roughly 3 gigahertz and so on. Indeed, when you look at the ground state, there's a splitting between this spin configuration where the two spins are, in the ground state of being anti-parallel to the state where they're parallel with one another of about 3 gigahertz. And so that's built in. You don't have to apply a magnetic field or anything. You automatically get a energetic ground state splitting. Now, one of these levels is degenerate. And suppose we just want to use two spins, like the two states of our coin. Well, the way we can do that is apply a magnetic field to Zeeman shift these two levels out of resonance, and then you can use, for example, the MS equal the magnetic sublevel 1 and the magnetic sublevel 0 as your two spins. And so, and then if you excite this thing, you get fluorescence out. And you can see the fluorescence spectrum here. Now this has this narrow zero phonon line, which corresponds to the transition from the lowest energy excited state down to the ground state. But it also has this ugly phonon sideband. And that phonon sideband corresponds to basically when the photon is released, another phonon is released into the lattice and it carries away some energy. So the photons here are a little bit redshifted. Now you can entangle this electron spin with a photon by addressing it with an energy that couples to only one of the magnetic sublevel ground state to excited state transitions. For example, in this case, it's tuned to the MS equal 1 ground state to excited state transition. So this laser light is absorbed and then scattered by that emitter, whereas if the state of the NV is in state 0, that transition is off resonant from that laser, and it won't scatter a photon. So here you have a way of entangling a state of a photon with a state of a spin. And you can use that then to entangle two distant electron spins. So for example, you can see that here, two electron spins each emit a photon or emit light into a mode, and then you measure that mode in a belt state, in an entangled basis. And if that belt state measurement succeeds, you've entangled the two photons, but since they are already entangled with two electron spins in the respective cavities, these electron spins are also entangled. In this way, you can then entangle two cavities. The nice thing about the NV is that you don't have just the electron spin, but there's a couple of nearby nuclear spins as well, like carbon-13 nuclei, which is spin 1/2, and you can use this as additional resources for your quantum network. Now this primitive link has been demonstrated already by the Ronald Hansen group at Delft University with an entanglement rate that's about 1 in 100 seconds or something like this. So that's slower than the coherence time of the electron and nuclear spins, which each are on the order of seconds. And so the problem here is that you can't entangle these things faster than they fall apart, than they decay. So it's like building a house of cards and everything is falling apart faster than you can put it back together. So what you have to do is find some way to make these optical interactions more efficient, and the cavity is a way to do that. So first of all, let's fix up that spectrum, that ugly spectrum. We can only use the photons in this coherent transition. So when you put an NV into a cavity, as we and others showed some time ago, you can dramatically change the emission spectrum so that almost all of the emission goes into the cavity and in the zero phonon line. So that's one way that you can do it. But the problem is that this thing had a couple of challenges. First of all, the yield of these devices was low. The NV in this case was spectrally unstable, and so there were a lot of problems with it. So over the years, we and others around the world have made more and more progress in making basically these cavities, these optical cavities, which are photonic crystals, more and more reliable so that the cavity fabrication and the NV fabrication is consistent. And this has really been a strong engineering effort. And so I wanted to show you the best result that we have nowadays. It's over here. This relies on, first, you start with a bulk diamond. You then produce a mask, and you etch that down into the diamond, some 100 nanometers or so distance. Then you deposit on all sides a conformal coating that protects the sidewalls from a subsequent non-directional an isotropic etch, oxygen etching, and that produces an undercut of this membrane. And this way, you're left with a freestanding rectangular photonic crystal, and these photonic crystals can actually have pretty good quality factors. I think the highest that we get in the field are something like 15,000, or nowadays about 20,000 or so, near the zero phonon line. And the beauty of this approach actually for us has been that it's really reliable. Like every time we do it, we can get thousands of cavities that work out. We've developed a number of other methods also to align NV centers to these cavities. So how good are the NV centers? So what we do is, not every NV center is alike, unfortunately. So we look through tens of thousands of NV centers and look for the best candidates. So you can see that here, this is a robotic microscope that works for like a couple of days to register actually hundreds of thousands of NV centers and looks at their spectrum and it looks at their spin properties. And we do the same thing at low temperature and we look at their optical line widths. And so you can see that in this case, where the NV centers are implanted about 100 nanometers underneath the surface, they can have pretty narrow transitions, like close to the Fourier transform limit. So that's actually a pretty good optical, they're pretty good optical emitters, nearly Fourier transform limit optical emitters. Then we position cavities or other devices over the best functioning emitters because we can also localize these in the microscope. So we fabricate structures over these localized emitters and look at the line widths then. And the thing is, for a long time, the line widths would get really, really broad, like gigahertz or something like this, so they were not usable anymore. But nowadays, we can have some of these devices that, this is very preliminary data still here that I'm sharing, but that have really nice narrow lines, like relatively narrow lines, like only maybe a factor of 10 away from the Fourier transform limit. So we're not yet there, but we're getting close to the point where we can fabricate structures over well-behaving NV centers, and they stay pretty well-behaved. Okay. That's part of the story. Next thing is you want to not just have one NV per site. You actually need to have multiple quantum registers per site for error correction. So you need some overhead capacity. So as we said already, the electron spin is one spin qubit. Then the nearby nuclear spins are maybe an additional 1, 2, 3, 4 nuclear spins. But actually for generalized error correction, we need at least 9 nuclear spins. And so we're working on implanting multiple NV centers close enough together so that they're magnetically coupled together. The electron spins are about 10 nanometers apart, ideally, so that the coupling rate between them is on the order of 10 or 50 or so kilohertz. And so you have to, this is a fabrication, this is a really difficult fabrication challenge. You have to get nitrogen atoms into a close proximity and not anywhere else. And so we, together with Shalom Wind at Columbia, fabricated these small apertures into which we implant nitrogen atoms and then convert some of them into nitrogen vacancy centers. And here you can see some preliminary results, which is a super resolution image of like one implanted region here, where you can see that through one of these holes, for example, we were successful in producing 2 NV centers that, in this case, are about 20 nanometers apart. So we're not yet there, but we're getting close to being able to produce small quantum registers, like a small quantum computer consisting of maybe 10 or 20 or so nuclear spins. That is an error-corrected quantum register that we need for these systems. So I just wanted to check with the organizers. How much time do I have left? 4 minutes. All right. So here's a different way of implanting. This here uses a focused ion beam. You can't, unfortunately, do focused ion beam implantation with nitrogen atoms, at least not yet. Some people do that, but not yet well enough because you need a solid-state source that produces, that evaporates nitrogen atoms. But you can do it very well with silicon atoms. And here our collaborators at Sandia National Laboratory implanted silicon vacancy centers directly into photonic crystals that we had given them. And we can put these silicon vacancy centers directly into the mode maximum of this, in this case, 2-dimensional photonic crystal. And the nice thing about silicon vacancy centers is that when you do this actually pretty reliably, the line widths are very narrow. So we can do that with a precision of about 40 nanometers, which is good enough for optical resolution for the nano cavity. And the line widths are close to the Fourier transform limit, about 126 megahertz, which is within a factor 2 of the Fourier transform limit. So these are really well-behaved color centers, but their spin isn't yet as good, so we're still actually primarily focusing on NV centers. Suppose that you can make these spin interfaces reasonably well. As I showed earlier, we want to put a couple of these NV cavity systems into these waveguide circuits. And so that might look like this. You have a number of optical switches with atomic memories connected to them, and the switches route light between memories on the chip. So I'm going to skip over that. Here you see that, you know, an early experiment from 2 years ago, roughly now, where we were integrating waveguides containing NV centers into a silicon nitride waveguide circuit. This is together with Mikhail Lipson's group at Cornell. And here you can see the waveguide circuit, silicon nitride, and these diamond waveguides integrated over it. And each of these waveguides was chosen to have a well-behaving NV center right in the middle, and only a single one with good spin and optical properties. So this is a way of assembling only the very best of spin quantum memories into our optical underlying circuit. Now, silicon nitride turned out to be problematic in two things. It's not an electro-optic material, it's passive, so we couldn't make switches very good. And the other thing is that it had some intrinsic background fluorescence. So we've, in the last couple of years, transitioned to aluminum nitride on sapphire, and here you can see just a snapshot of just unpublished work that shows the sort of architecture of aluminum nitride and sapphire that we're building. And this is the mode profile that you can see here for light at 640 nanometers. You can put in Bragg filters, ring filters. Together with Carl Bergen's group at MIT, we've integrated superconducting nanowire detectors and so forth. So basically, this is the underlying platform that we then want to populate with these NV-containing diamond waveguides or cavities, and you can see one of them here. Okay, so you know, this is what the circuit here is showing. It's just an initial trial circuit. So it's a relatively simple circuit. Pump light is distributed amongst, in this case, 1, 2, 3, 4 NV centers, which are in tunable cavities individually. Then there's tunable ring filters, and then there's this interferometer here that's used to route light into a common photodetector for the heralded entanglement that I already showed you. We don't yet have that circuit. I think we're reasonably close. We don't yet have it. But we're guided in this work by our work in silicon photonics again. So silicon photonics is this beautiful platform that people have developed. I'm really grateful to the pioneers in that field. That's now available from foundries. And so you can make switch arrays in silicon photonics that are really large. In this case, this is a switch array that we've built together with Michael Hochberg and Tom Baer-Jones at OPSIS that has about, you know, close to 100 Mach-Zehnder interferometers with 200 or so individually controllable phase shifters. And so that's a completely tunable, sort of an optical FPGA, if you like. And it's really helping us a lot in designing this sort of parallel thing in our much more primitive platform of aluminum nitride on sapphire. All right, so one last slide about how we go from, where we go from here. Suppose that, you know, in 5 or 10 years, you have a reasonably well-working quantum repeater. So you can maybe build these networks. But there's another exciting opportunity, which is to connect a bunch of these small quantum repeaters into a sort of a network quantum computer system. And this is the idea of a modular quantum computer. And so the key challenge in these modular quantum computers is to build entanglement across many, and I'm talking about hundreds or thousands of qubits fast enough so that you can use it before it decays. So it has to be a very fast way of producing this entanglement. And in this paper, we're analyzing a way that uses percolation to entangle nearby electron nuclear spin systems that are indicated in these circles. Whenever we succeed, there's a line drawn between them. And percolation theory tells us that if in a square lattice, the probability of drawing these lines is over 50%, then you suddenly have this emergence of long-range order. And everything is connected with high probability. This is percolation threshold. This is a classical thing, but it's really nice. Also works in quantum. And so if the efficiency of producing these nearby links is high enough, then you have this large entangled state that you can use as a resource for modular quantum computing. And the nice thing, and I want to just point you to this reference, is that this work shows that we can probably produce this long-range entanglement if our qubits are well-behaved in something like 100 microseconds or so. And that's much shorter than the spin coherence time of the individual spins. So that makes us hopeful that maybe we can, in fact, build these sort of large-scale cluster states for modular computing. We've done similar work that, that's also interesting for networks in using just a large number of photons for photonic cluster states. Another avenue besides superconducting detectors is to use graphene single photon detectors. We're excited about that. I'd love to talk to people about that. There's a recent paper we have in the archive on this. And we're also interested in using the sort of new designs that are described in these papers here for achieving even stronger, higher per cell coupling between NVs and photons. So with that, I get to my summary. So I've talked to you a bit about, how far can we go using only photons in building quantum networks? And it's not that far, hundreds of kilometers. How can we go further? Well, for that, we need, as far as we know, quantum memories. And so I've shown you one of the ways of doing that with NV-based quantum memories in Diamond. And then I think there's this pretty big opportunity to, once we have these systems, to think about stringing them together fast enough so we can build general purpose quantum computers. So with that, again, I want to acknowledge everybody who contributed to this and thank you for your attention.
I don't think so. Okay. Thanks for a very nice talk. And are there any questions? Oh, yeah. Okay.
Giving our chair some exercise.
I'm just curious on your opinion of how and where metamaterials might fit into this.
Yeah, I think there's a couple of areas actually. For one, some of the metamaterials and photonic crystals and so on that are being developed are really critical for making our spin-photon interfaces efficient. There's metamaterials, for example, for diffractive optics that I think could play a big role in solving some of the optical challenges. We don't just need lenses anymore. We need, for example, devices that are very compact multiplexers, as an example. So if there was a metamaterial device, and people are working on this stuff, where you can, in a small footprint of maybe 20 by 20 microns or so, split light with high extinction into the red and the infrared spectrum, that would be of really great use for us. The devices I showed you, for example, for splitting the zero phonon line from the phonon sideband, these ring filters have the downside that they're relatively large and temperature sensitive. So if we could have materials that produce, temperature insensitive multiplexing, demultiplexing systems that are compact, that would be a huge advantage. So I think basically the answer is there's a strong need for new kinds of nanophotonic elements to realize the demands that are really hard on building large-scale components for repeaters and for computers.
Okay, last question here.
Just short question. And what is a probability of having a bit error and just delay based on your experiment?
The question is about what is the probability of bit error?
Yep. And then delay based on your experiment, like 120 kilometers, something like that.
Oh, I see. Yeah. So in our case, the furthest that we've gone is 42 kilometers with an equivalent fiber distance of about 80 kilometers, given a 15 or 16 dB channel loss. And in our case, the bit error rate is, in our case, with the absence of an eavesdropper who's messing with our system, which we don't simulate, is less than 1% bit error rate. Okay, I think we should probably...
Okay, thanks very much for nice presentation.